All right, today we are going to start our look at logarithmic functions, and I've grouped the first two objectives together before we start. The first of our objectives is that we will change exponential statements to logarithmic statements and logarithmic statements to exponential statements. Obviously, this lets us know there's a strong connection between exponential and logarithmic statements. The second objective is that we will evaluate logarithmic expressions. And I'm going to put that together because knowledge of the first objective ties directly into the second. When we begin to explore logarithmic functions, we're going to start with our knowledge of exponentials. So remember that the exponential function f of x equals a to the x is 1 to 1, and therefore it has to have an inverse function. So I'm going to begin our exploration today with the function f of x equals a to the x. Remember, a is greater than 0 and it's not equal to 1. We put both of those qualifications in when we studied exponential functions. If I want to take the inverse of this function, what should I do? I'm going to write it as y equals, just for the sake of neatness. And then the most important step is I'm going to interchange my x and y variable. So the inverse of my exponential function is x equals a to the y. Now normally if we were working with this, our next step would be to isolate y. But we do not have any of our current algebraic skills available to solve for this y variable. We don't know how to isolate a variable that's in an exponent. And this is where logarithms come in. So we are going to need to define the concept of a logarithm. Without that concept, we're unable to isolate y in that equation. When I show you the definition of logarithm, it may not look like you're expecting. I'm not going to define it in words. This isn't going to look like Webster's dictionary. Instead, we define a logarithm with two equations. And this is our definition for a logarithmic function. Right? The equation y equals log base a of x is true if and only if x is equal to a to the y power. Remember that if and only if phrase when we learned about biconditional statements. Sometimes we can represent that with a double-headed arrow. So if you look at these two equations that we have written here, if one of them is true, then so is the other. That's our definition of a logarithm. Now I know that's a little strange. Again, we didn't define it verbally, we defined it with equations. But if this is how we define a logarithm, then if we look back above where we said the inverse of our exponential function was x equals a to the y power, if that is true, then by our definition of a logarithm, then y is equal to log base a of x. And this is our definition for the logarithmic function, this if and only if. Two important facts for you to know about logarithmic functions. First of the two, a logarithm is a name for a certain exponent. So we can see that back here in the definition. The logarithm is the name for y, and y is the exponent in the other equation. Second thing that's important we understand, if we look at the expression log base a of x, know that it represents the exponent to which a must be raised in order to equal x. So when I look back here, log base a of x, know that that means the exponent to which a must be raised in order to equal x. And that's our definition of a logarithm. Pause the video and take some time to make sure that you understand the inverse of an exponential function, the definition of a logarithmic function, and these two important facts. After using our definition of a logarithm, we see example 1 here gives us an equation y equals log base 3 of x. And according to the definition of a logarithm, I can rewrite that in an exponential form. Remember, what this means is The logarithm is the exponent to which I must raise the base 3 in order to equal x. So y, being equal to the logarithm, is the exponent I put on the base 3 in order to equal x. How about if I look at 4 equals log base 3 of 81? In this case, that means 4 is the exponent that goes on the base 3 in order to make the power equal 81. So I can write this showing that 4 is the exponent on the base 3 that makes my power equal 81. Let's consider this one. Y equals log base 5 of x. If y equals log base 5 of x, that's a way of letting us know that y is the exponent that goes on the base 5 in order to make the power equal x. If you use that knowledge in this specific example, I tell you negative 1 equals log base 5 of 1/5. What does that mean? That means that negative 1 is the exponent that goes on the base of 5 in order to make the power equal 1/5. And that's how the definition of logarithm works for us. Okay? In the next couple of examples, I'm going to give you an equation in either exponential form or logarithmic form, and we're just going to change it to its equivalent form. So here's our first example we're going to look at, example 2a. Okay? In example 2a, I'm giving you an exponential equation. I'm saying 1.2 to the third power is equal to m. If I want to write that as a logarithm, that means that this 3 is the exponent that goes on the base of 1.2 in order to make the power equal m. Compare what you see in these two steps to the definition of logarithms that we wrote down before, the if and only if. We can use that definition to do further examples. Take a look at examples B and C, pause the video, and try and write those as a logarithmic equation using the definition. All right, in example B, we see that B is the exponent. So a logarithm, if you'll remember, is the name of a certain exponent. So B has got to be equal to a logarithm. The base is e. The base from our exponential is also the base in our logarithm. And what this now says is when I read b equals log base e of 9, it tells us that b is the exponent that goes on the base e to make the power equal 9. Some of you know a shortcut for writing a logarithm whose base is e. We will talk about that soon, but not right now. Checking example C, 4 equals a logarithm base a of 24, because 4 is the exponent that one would write on the base a to make the power equal 24. In our next example, all I'm going to do is begin with the logarithmic equations and have you write the exponential equations. Again, go ahead and pause the video, use the definition of logarithms to rewrite these equations without logarithms. All right, we're back. Let's take a look at our first logarithm here. So our base is a, and remember that a logarithm is equal to a specific exponent, in this case 5. What that tells us is 5 is the exponent that you would put on the base a to make the power equal 4. According to the definition of logarithms, If this first equation is true, this second equation is true. You can check your answers for B and C using similar knowledge. In our fourth example, we're going to go into objective number 2, which was that we could evaluate logarithmic expressions. So here are two expressions for us to evaluate. Example 4a wants us to evaluate the expression log base 2 of 16. Now what does that mean? If we examine log base 2 of 16, for us that means that we're asking us a question, to what exponent must 2 be raised to equal 16? Remember, a logarithm is a certain exponent. In this case, it's the exponent that we must place on the base 2 to make the power equal 16. So if I want, I can write this as an exponential equation. We've already studied those. I'm finding an unknown exponent on the base 2 in order to make the power equal 16. I'll write both expressions as base 2, so that 2 to the y power is equal to 2 to the 4th power. If two equal powers have equal bases, they must have equal exponents. So y has to equal 4. Therefore, the expression at the very beginning, log base 2 of 16, that was searching for which exponent you must place on the base 2 to equal 16, is just 4. 4 is the value of that exponent. Right. Pause the video if you need to make sure you have that written down. All right, now let's look at example B. Log base 3 of 1/27. Again, why don't you pause the video here and try this one on your own. All right, I hope you gave example B a good shot. Log base 3 of 1/27 is just asking the question, to what exponent must 3 be raised to equal 1/27? So we're searching for a certain exponent. In order to find that exponent, I could write an exponential equation. 3 to an unknown exponent equals 1/27. I can write both expressions with a base of 3. 3 to the y power equals 3 to the negative third. Remember how negative exponents are used for reciprocals. Obviously, if two equal powers have equal bases, they must also have equal exponents, so y equals negative 3. We have found the exponent that you must place on the base 3 in order to make the power equal 1/27. Pause the video again here and make sure you have example B in your notes. All right, the last objective we're going to look at today as we learn about logarithms is we're going to learn to determine the domain of a logarithmic function. Okay? This will be the third domain rule that we have learned this year. We have spent much of this year knowing two domain rules. The denominator of a rational function cannot equal 0, and the radicand of a radical function with an even index must be greater than or equal to 0. Today we learn our third domain rule. So to determine the domain of a logarithmic function, let's remember that we started our study of logarithms by learning that they are the inverse of an exponential function. So I'm going to write down our standard exponential function, y equals a to the x, where a is greater than 0 and not equal to 1, reminding you that the domain of the exponential function is all real numbers, and the range is 0 to infinity. The logarithmic function is the inverse of the exponential function. Remember that when we studied inverses, we learned that the domain of a function is the range of its inverse. And the range of a function is the domain of its inverse. So in this instance, y equals log base a of x, the domain is from 0 to infinity, telling us that this x value right here must be what kind of number? Positive. We know that this x value is positive. In a logarithmic function, we can refer to this quantity as the argument. So this is our third domain rule of the year. We're going to remember this just like we do those other two we've been working with. The argument of a logarithmic function must be greater than 0. That is our third domain rule. If it helps you, for your initial practice, every time you use that rule, write it down. So let's take a look at an example. We're going to look at 3 different functions and find each domain. The first is f of x equals log base 2 of the quantity x plus 3. The quantity x plus 3 is our argument. What's our domain rule for the argument of a logarithmic function? The argument of a logarithmic function must be greater than 0. So we can state that that quantity x plus 3 must be greater than 0. As a linear inequality, we can solve this by subtracting 3 from both sides, and we end up with x is greater than negative 3. Almost made a mistake there. That means that our domain contains all of the values between negative 3 and infinity. Notice this is an open interval because the argument may not equal 0, and therefore negative 3 is excluded from our domain. If you need a moment to pause the video and make sure that you have this important rule about the domain of logarithmic functions and example A done, go ahead and pause and write them down now. Okay, next example. In example B, our argument is now a rational expression. So we have g of x equals log base 5 of the quantity 1 plus x over 1 subtract x. Again, think about our domain rule for logarithms. The argument of a logarithmic function must be greater than 0. Therefore, I know that that expression, 1 plus x over 1 minus x, must be greater than 0. Recently, we learned that to solve a rational inequality requires critical values. If I simply multiply both sides of the inequality by this denominator, I will lose part of my solution. Instead, the definition of the critical values of a rational expression are the real zeros of the numerator and the real zeros of the denominator. So setting each of those equal to 0 gives me that the critical values are negative 1 and positive 1. Then remember, I take those critical values, I plot them on a number line. I know that negative 1 is not a solution to this inequality because I do not want the numerator to equal 0. I also know that positive 1 is not a solution because if the denominator is 0, this expression is undefined. Sorry. Identify your 3 intervals as you break the real number line up at the critical values. Choose a test value in each interval. I've chosen negative 2 in the first interval, 0 in the second interval, and again I notice a mistake here. That second interval runs between my 2 critical values, negative 1 and positive 1. And I've chosen the test value 2 in my third interval. Evaluating the rational expression at each of those leads me to conclude that in the first interval, the outputs are negative, in the second interval, the outputs are positive, and in the third interval, the outputs are negative. Since I need that function to be greater than 0, I need the interval that leads to positive outputs, negative 1 to positive 1. So the domain of this logarithmic function up here is values from negative 1 to positive 1. Again, an open interval. All right, one last example about domain. The last example we're going to look at, function h of x is equal to a logarithm base 1/2 of the absolute value of x. Our rule states that the argument of the logarithm must be greater than 0. In this case, the absolute value of x must be greater than 0. It's been quite a while since we solved an absolute value inequality. Remember, there are two situations that may be true. If x is positive, then taking the absolute value of a positive does nothing to it, and I just have that x is greater than 0. However, we have an or here because it could be that x is a negative number. And to take the absolute value of a negative number, I need to multiply it by -1. So then I get negative x is greater than 0. To solve this inequality for x, I have to divide both sides by -1, which flips my inequality sign. There's something to remember from your past. Obviously, 0 divided by -1 is still 0. So this is true if x is greater than 0 or if x is less than 0. I hope that makes sense when you look at the absolute value of x, and you understand why that any number greater than 0 or less than 0 has an absolute value that's positive. Therefore, the domain of this function is -infinity to 0, union 0 to infinity. Both intervals are open yet again. Take a minute to see why 0 is not in the domain. All right, that's a good introduction to the definition of logarithmic functions. It gives you an understanding of the connection between exponential equations and logarithmic equations, and you've learned a third domain rule. You've learned that the argument of a logarithmic function must always be greater than 0. I hope this video has helped you to understand logarithmic functions a little better. You now will have an opportunity to practice them on your own to strengthen that knowledge. Have a great day.